So we have switched the interventions, and we are starting with Pratyush Pranav.
So, Privyet and hello, and thank you for inviting me again. It's been a long time since I saw you guys. And without wasting much of your time, let's get into the talk. So, today we will be using the concepts of geometry and topology in the context of cosmology. And I'll be departing a little bit from the standard format in the sense I don't have theorems to prove here. So I'll talk a little bit about the background and then I'll show you some results. The outline of my talk is I'll give you a little background about the cosmos, the universe, what we know of it till now, and what the cosmological principle is. Then we will go into the data sets that we encounter in cosmology, and that we will root through the idea of random fields and excursion sets. Then I will talk about geometry and topology, and then we will combine all of this to use the methods on cosmic microwave background data to see whether we can test the fundamental tenets of cosmological principle, and then I'll conclude. So start with the universe, give you a little bit of a history of what we know till now about the universe according to the standard cosmological model. As we understand, the universe started in a hot Big Bang. This is something that's sort of well established. There was a big debate about it for a long time between whether the universe had a start or whether it's infinite and it's been going on forever. And this debate was settled by a mathematician who used to be a monk in a Belgian church. And in fact, the name Big Bang, it started as a joke on BBC Radio. And till it got vindicated by the observation of the cosmic microwave background. The priest, the gentleman who gave the idea of a hot Big Bang, his name is Georges Lemaitre. And because Georges Lemaitre happened to be a priest, it sounded like this was the church's propaganda to talk about creationism. So Georges Lemaitre was looked down upon quite a long time. And in fact, after 30 years of his death, is when two engineers from NASA, they accidentally discovered the cosmic microwave background. They were not looking for it. And that vindicated Georges Lemaitre, and then the Big Bang model became the standard cosmological model. But Big Bang is not the only part that is a part of standard cosmology. There are a few other things that come in. So Big Bang is about whether things began or not. Then we can also ask about the size and shape of the universe, like the bigger, the grander scheme of things, whether the universe has a particular size and shape. Then we can also talk about how matter is distributed in the universe. And all of this combined together to form the standard lambda CDM, lambda cold dark matter paradigm of cosmology. That's the standard cosmology. The idea about roughly what we understand of the universe till now, it started as in a Big Bang. Then there was a brief period of something what we call inflation. This has not been tested yet, but it answers a lot of open questions in cosmology. For example, the horizon problem or the magnetic monopole problem. I'll not go into the details of these things, just suffice to say the name. And then we have an event called the appearance of light. So as it's written in Bible, let there be light, and there was light. This happens 2 times in the universe. The first time light appears in the universe is the appearance of the cosmic microwave background. This is when a proton and an electron combines together to form a neutral hydrogen atom, and then the light from the Big Bang, the original Big Bang light, it is streaming freely in the universe after that. Then we see from cosmic microwave background to the first stars, there is a period of dark age because the matter is mostly neutral. It's well dispersed in the universe. But eventually, through the action of gravity, matter starts clumping together and it ignites again. And that ends the dark ages. And then we have the first stars that are born. Those stars then gradually form the galaxies. And eventually, we are here about 13.7, 14 billion years after Big Bang. In between, about 7 billion years after Big Bang is when we notice that the expansion. So Hubble he noticed that the universe is expanding. In fact, that is what led Georges Lemaitre to coin the hypothesis that if things are expanding, and if they're expanding everywhere and you're in the center, then going back in time, they must have been together. And that's where he got the idea of the primordial atom, that the universe started in a point, though the meaning of that point is a little philosophical. So that's the creation of space itself, space and time itself, as we understand. So now, what is the cosmological principle? This is the basis on which we understand. So at some point we have to make some guess because we do not know about things. And the basic guess of the universe, the idea starts from the Copernican principle. So Copernicus comes and he says, Earth is not the center of the universe, Sun is. Then we can relax that and we can say there are no centers in the universe, there are no preferred directions, there are no preferred locations. Mathematically, we call these properties the property of isotropy and the property of homogeneity. So isotropy means there are no special directions in the universe, no directional dependence. Homogeneity means there is no special location, so everywhere is more or less the same. Statistically, that does not, so if we are sitting in our solar system, it does look like it's not statistically homogeneous. So we are also talking about some scale over which things start looking homogeneous. On top of that, the theory of inflation says that the initial primordial fluctuations, they are of a Gaussian characteristic. So together, the theory of inflation, isotropy, homogeneity, and the Gaussian nature of things is what gives us the standard cosmological model, that there are no directional dependence, there is no location dependence, and on top of that, the fluctuations in the universe are an instance of a Gaussian random field, an isotropic and homogeneous Gaussian random field. This gives us sort of a benchmark on which to base and to test the observational data that we have. And the cosmic microwave background, it's the earliest and the largest canvas on which we can test the cosmological principle. And my talk is going to be in that direction today. If we can use these methods of geometry and topology to be able to see if we can say something about the characteristics of the matter distribution in the universe through the cosmic microwave background, even though cosmic microwave background is rather a map of light. But light is very intimately connected to the matter distribution in the universe. So when a photon was in a potential well of matter, it requires some energy to escape, and then it gets a little redshifted. On the other hand, if the photon is on a potential hill, then it gets an extra boost and it gets blue shifted. And that's what we see as the map that we measure. Say the latest map that we have of the cosmic microwave background, this is the latest map. This is from the Planck satellite. And the blue regions and the red regions, these are basically mapping with the matter distribution, the underdensity and overdensity of the matter in the universe at the time of the cosmic microwave background. This is about 380,000 years after the Big Bang. And so given this background of cosmology, now we talk a little bit about the kind of data that we encounter in cosmology. And mostly these are instances of stochastic fields. This is a random field. So the idea of random fields and random functions are very useful in trying to understand the statistical property of the matter distribution in the universe. So either the data that we have is continuous or discrete, but our measurement is mostly discrete in the observational context. And so a natural choice of examining the stochastic nature of some field is to look at the properties of random fields. And the properties of random fields we examine through something called an excursion set. This is the standard process on which we can apply geometry and topology. The idea is that if we have a random field on a parameter space M, then the natural choice is to examine the image of the parameter space or subset so that we have with the mapping that there is a function defined on the manifold and it maps to an RD functional space. Then it would be natural to be able to express the quantities in terms of what we are after is a closed form analytic expression. in which case it would be natural to express the structure of the function on the manifold Fm as a combination of the topological structure of the manifold, the probabilistic structure of the function f, and the ambient dimension of the manifold. But despite this general obviousness, there are no results in this direction. What we can do, though, is ask an inverse question. The inverse question is to examine sets in the parameter space where the function takes particular values or it exhibits some specific properties. And these are known as the excursion sets, defined in the following form. And when the dimension d equal to 1, so the function is a real valued scalar function, and h is going from some particular threshold to infinity, this is called the hitting set. Then we have the excursion set defined as the following. So pictorially, what this means is, let's say on the right-hand side, you see this is the simulation, like we simulated the cosmic microwave background. And we start from a very high threshold. And as we bring our threshold down, we look at how the function defined on this manifold is connecting the manifold. So the properties of the manifold, they are defined by the function that is defined on it. So at some point, we will see some isolated objects appearing in our excursion set. Eventually, those isolated objects, they will merge together, and then these isolated objects and these mergers, and they will also form holes. This is in the context of the two-dimensional surface of the sphere. When they form holes and these connected components, these are described in terms of topology. But not only that, we can ask questions like, what is the area? What is the perimeter length, and so on and so forth? All these are geometric and topological notions, which brings me to describing them next. There are various ways that we can approach geometry and topology, but the kind of geometry and topology that I'm interested in, it's arising from something called the Minkowski functionals, which are known by various names. And in various settings, they have various names, like Wehrmass integrals, Dehn and Steiner polynomial, intrinsic volumes, and Lipschitz-Killing curvatures. And these are d+1 quantifiers for a d-dimensional set. It's a closed thing. The way I want to define, we only need Minkowski functionals and Lipschitz-Killing curvatures for the definition, which when defined properly, they are related by this expression. So the jth Minkowski functional is related to the d minus jth Lipschitz-Killing curvature, where omega k is the volume of the k-dimensional unit bond. And that's the definition, but in practical situations, when we have a convex body, a nice way of defining it is via the Steiner formula or the Wales tube formula, where the d-dimensional volume of a manifold is written in terms of it's a truncated series. And so it's written in terms of all the Minkowski functionals, all the Lipschitz-Killing curvatures. This is the tube formula. So the left-hand side is known as the tube around M, and rho is typically small. In this case, it's trivial to check that Q0 and LD measure the d-dimensional volume of the set. Q1 and twice of the Lipschitz-Killing curvature L2 measure the surface area. The other functionals are a little bit difficult to define, but it's always a very true and a deep result that something called the Euler characteristic, chi, is always equal to the 0th Lipschitz-Killing curvature, and it is equivalent to the dth Minkowski functional. In that case, in 3 dimensions, we are left only with defining Q2 and N1. If the manifold is convex, then Q2 L1 or Q2 over 2 pi is twice the caliper diameter of M. The caliper diameter of N is, imagine a convex body, we take all the possible rotations of the object and look at the diameters and we average it, and that's the caliper diameter. So these are mostly geometric objects, except Euler characteristic, which is a purely topological notion. Now, there is a very deep result through Gauss, which is the Theorema Agrarium of Gauss, that talks about the connection between geometry and topology. This is the Latin for remarkable theorem, and it states that the Gaussian curvature of a surface is an intrinsic invariant. It is meaning that it is constant, irrespective of how we bend or twist the surface. So this is a global measure of the surface. And this leads to the Gauss-Bonnet theorem in 2-dimensional case, where we have the Gaussian curvature and area over the manifold. And if If the manifold is not compact and it has boundary, then there is also a boundary element that comes in. And so the left-hand side, as you notice, is a totally geometrical quantity. It's an integral geometric quantity. On the right-hand side, we have something called the Euler characteristic. It's a number. It's an integral number. So now we understand that this is how it happens, but it's not so obvious that something that is a purely geometric notion, like the Gaussian curvature or the integral of the Gaussian curvature, could relate to something which is of a purely topological nature. And this is why it's called the theorem agrarium, or the remarkable theorem. The Euler characteristic is originally, so now we will define a little bit of what these notions mean. The Euler characteristic was originally defined for polyhedra. And what Euler noticed is that for a convex polyhedron, there was a sum which is invariant, and that sum is this quantity here, which is the number of vertices minus the number of edges plus the number of faces. For a convex polyhedron, it always comes to 2, and this is what Euler found. The modern definition of Euler characteristic, though, comes from through algebraic topology, homology theory. And so there are various ways that we can arrive at this notion of Euler characteristic. It can be the alternating sum of the critical points of different indices, or it can be the alternating sum of the simplices, different dimensional simplices. It can also be the alternating sum of something called the Betti numbers, which is the homological direction that we will be using in this paper and mostly going in that direction. So Euler characteristic is very interesting. This is like, even though I will be only using Euler characteristic while showing the results, and those results will be from some previous papers that have analyzed the cosmic microwave background, so that what I'm going to show you is a little bit controversial, so I don't want to take it all on myself. And I would show you that there are things that have been done. There has been analysis of the cosmic microwave background in terms of Minkowski functionals and Euler characteristic. And there have been hints of certain kinds of deviations from the cosmological, some tenets of cosmological principle. So suffice to say that Euler characteristic is a very fundamental and central quantity in geometry and topology both. That brings us next to, are there things that are beyond geometry and topology, beyond Euler characteristics? It's funny, in applied sciences and in cosmology specifically, we are always looking for new kinds of statistics that we can use to be able to see if there are differences that we can come up between data and model, let's say. So as we can understand, two different manifolds can have the same Euler characteristic, but they may not have the same topology at the level of homology, if we are talking about. And the reason and rationale to look for beyond the genus Euler characteristic and Minkowski functionals, I talk in terms of cosmology because historically Minkowski functionals has been used in cosmology a lot. Also because there are closed form analytic expressions available for Minkowski functionals of Gaussian and Gaussian related random fields. This is through the work of Adler and his collaborators. This is the Gaussian kinematic formula. That is by now in a very advanced state, and whether it's a Gaussian field or somehow related to a Gaussian through some sort of a transformation, in these situations we have a closed form analytic form. These are important, especially in cosmology, going through the standard cosmology. Then once we have an analytic form, then we know that we can go the route of parameter estimation through these analytic closed form expressions. And this is a very important cosmological direction, to be able to estimate the parameters governing the equations of the evolution of the universe. So the reason beyond this is genus. It's defined only for a closed two-dimensional surface, and it has no generalization in higher or lower dimensions. Again, the Euler-Poincare formula states that the Euler characteristic is the alternating sum of another topological invariant called the Betti numbers. This should already tell us that if there is an alternating sum, various quantities coming together as an alternating sum can result in the same number. Say, for example, if I said 1 minus 2 plus 1, it ends in 0. 2 minus 4 plus 2, it ends in 0 as well. all of these two things, 1 minus 2 plus 1 and 2 minus 4 plus 2, this, as we will be seeing, is that they represent another level of topological information. So manifold, which may be similar, the same, having the same two manifolds, having the same Euler characteristic, may be different in terms of their topology, in terms of something called the holes that they contain. On top of that, a formalism that is capable of expressing topology in a hierarchical fashion is very interesting for cosmological datasets, because we understand that the matter distribution and the structures that form in the universe, they go in a hierarchical fashion, in the sense that smaller objects form first and they aggregate together to form larger and larger objects. If we can have a method that can tell us more about this hierarchical aggregation, then this is a powerful extension for describing the geometry and topology in the cosmological dataset. I also write biology because recently I've started looking at organization of biological systems as well. So that brings us to the main theme of my talk here, which is homology. So homology is the description of a topological space in terms of cycles and boundaries that it contains. And so it enumerates a topological space in terms of holes of different dimensions that it might have. And the fundamental lemma of homology, how it works is with this fundamental lemma that the boundary of a boundary is always empty. Intuitively, what it means is that, say, for example, when we have a two-dimensional spherical surface, it's bounding a three-dimensional void. A ring, it's bounding a two-dimensional hole. And these boundaries are what we are after, because they tell us about the holes that we capture. These are all topological notions. So holes can also be understood in terms of, let's say, like you cannot contract a space to a point if there is a topological hole in that space. These are things that are interesting and essential to be able to define the characteristics of the space that we are dealing in. I will not go into details, but the way homology works, going into the simplicial direction, is that this is also called algebraic topology. So there is sort of a group structure. Homology, we form homology groups. So there is a chain group, and then the subset of a chain group, a particular kind of a chain group is a cycle group. A particular kind of a cycle group is a boundary group. A cycle may not always be a boundary, but all boundaries are cycles. And then we define the pth homology group. So a p-dimensional chain is a formal sum of p-dimensional simplices, and this could be over a coefficient of ring, field, or Z2. Mostly we use Z2 for our computations. A p cycle is a boundary of a p plus 1 chain, and in this direction, a zero cycle is a closed component, a one cycle is a closed loop of edges, or its finite union. Similarly, for two cycles is a closed surface, or its finite union. Mutually homologous p cycles, they give us the p-dimensional class. This means, let's say, one ring around. If we look at this torus, for example, and I see there is a blue ring here that defines a cycle, but there can be infinitely many such rings around, and they are all mutually homologous, and they give us the homology group, basically. So collection of independent p-dimensional classes is the homology group HP. And the Betti numbers are the rank of the homology group. So the Betti numbers count the number of independent p-dimensional holes in a topological space. We talk about this torus in that case, because the torus is a single connected object. We have 1 0 cycle. So the rank of homology group H0 is 1. There are 2 1 cycles. Take my word for it that this is an empty torus. So we have, it's like a bicycle tube, not a donut. In which case, there is a hole here vertically, as you see, that we can pass in this direction. There is also a hole inside the tube. This is a one-dimensional cycle because we can go around with infinite multiplicity here. There is also a
Pratyush, can you come to a quick conclusion, or do you need some more time?
So like then I'll keep the background short now, and regardless, I'll try to finish it fast. So we talk about holes and how they form, and the idea is to be able to see how these topological cycles form and destroy as we bring our level set down and through the excursion set. That is the basic mathematical background. And then we form a persistence diagram, we compute the Betti numbers across different thresholds, and we look at the. So what we can do is, because we understand our standard cosmological model is isotropic and homogeneous Gaussian random fields, we extract the power spectrum from the cosmic microwave background. And because our base model is an isotropic and homogeneous Gaussian random field, all the information we surmise is contained in the power spectrum. And then we inverse Fourier transform or inverse spherical harmonic transform to generate many realizations of the field that we think is the right field. And with this background, now let's look at the results. I will show you results from in a chronological fashion, the way I looked at the data, the way I analyzed. And to look at the thing, we invoke something called relative homology. Relative homology, this is also because not every region in the sky always has good data. Some regions in the sky may not have data at all. So for example, when we are looking at the cosmic microwave background, there is a band around our galaxy that does not contain data. So how to do homology in presence of missing data? This is called relative homology. We mask those areas and then we compute the homology of the excursion sets relative to the masks. And this I will not go a lot into detail. So Planck data is specified on S2 as a deviation from the base temperature, and we look at these fluctuations. In some regions, we do not have data. We mask those data sets. At the highest resolution, we have at the moment about 55 million data points. So this is truly big data that we are talking about. And persistent homology computation takes about 150 gigabytes of RAM. So if I have to do a whole set of simulation, let's say on a statistically reliable direction, then maybe 1,000, 10,000, this would take 103 terabytes of RAM running for a few months. That's the kind of computational resources that we are talking about. And so we look at the cosmic microwave background, we smooth it at various scales. The reason why we smooth it at various scales is that maybe there is a scale-dependent physics that may be involved in there. And that's what we want to look at also. So for over the full sky, this is the Betti number graph that I get. So on the horizontal axis, this is the normalized threshold. The normalized threshold is like we compute the mean of the temperature variation, we compute the standard deviation, and we at every pixel, we remove the mean and we rescale by the standard deviation. This is at 5 arc minutes, 10 arc minutes, 20, 40, 80. 80 is a very interesting scale. 80 arc minutes is roughly a degree. And a degree is roughly the scale of horizon that we see now on the sky, which was at the time of the cosmic microwave background. So whatever was the size of the causal horizon in the cosmic microwave background, it extends roughly a degree in the sky of what we measure right now. I want you to remember this because we will see something interesting happening later. In general, for the full sky Betti zero, not too much difference. Here is the statistical variation of the Betti numbers. So roughly around 2 standard deviations, and at degree 128.80 arc minute, it goes a little bit above 2 standard deviations. Not very interesting things to note. Then when we look at the loops, the beta 1, around 5 degrees and larger, we have 3.5 to 4 standard deviations difference between the model and the simulations. But then again, we also do some statistical tests. We take into account all the thresholds across all the different smoothing scales to see if we are taking care of also random statistical fluctuations. We do not want that we go into the look elsewhere test and there could be a genuinely random statistical fluctuation which might appear to be serious when we are testing across multiple data sets. So multiple testing, to account for multiple testing, we go into we go into looking at things across various thresholds and smoothing scales. And what we get is that the summary that tells me is that there is a difference between the observation and the simulation. And there are also differences at some particular scale of 5 degrees. This is for the full sky. Now, full sky, 5 degrees, we don't have a lot of data. As you can understand, 5 degrees smoothing, the number of data points that we would have, the Betty numbers that it would not be a lot. And when we are after whether there is a difference between the observation and the simulation, and especially if we are after whether the cosmological principle is correct, we would not take this very seriously. At least I would not take this very seriously. Then what we can also do is, because now we are looking, now there is a difference that we noted. Now the next thing what we can do is to test statistical isotropy, whether CMB is looking the same in all the directions or not. One way to do it is to, let's say, mask all the southern CMB data and look at the northern hemisphere and compare it with the simulations, and same for the southern hemisphere as well. This is where things start turning very interesting. The top two graphs that you see over here, this paper has been published recently after a year of back and forth with the editors of the journal. The northern hemisphere, both the Betty 0 and Betty 1, they are going in general very significantly different from the simulations. In general, a 2 sigma deviation, but around a degree scale, this reaches up to 3.5 to 4 standard deviations. In contrast, southern hemisphere is extremely consistent with the simulations. Now, so when we have the same data, when we have the full sky simulation, when we see a 4 standard deviation, we can always say maybe it's an extreme realization of the same data set. But when we have a difference in the northern hemisphere and the southern hemisphere, this argument actually falls flat that there is extreme difference. So it is a hint of breaking of isotropy in the cosmic microwave background at the level of data at least. And so how much time do I have now? Do I have still 5-10 minutes or?
Yes, yes. Also because
Oh,
it was my fault that we waste some minutes.
no worries, no worries. So I'll just try to keep it fast and short. So this is what, and to look at the structure, we see over here that there is a 3.5 to 4 standard deviation, and this is across multiple data releases of the Planck data set. So we notice there is some sort of a consistency. We can also look at the structures. In general, maybe I should not ask a question, but one of them is a simulation. Now, one of them is the observation of the structure in the observational cosmic microwave background. The other three are simulations. I'm not going to make you make a guess. I'd answer it myself. If you look at the topmost is very fragmented as we see. So there are multiple isolated objects. On the other hand, the other three, they exhibit long range structures. The structures are larger. So even visually, we notice that there is a difference in the structure of the cosmic microwave background at the level of data and simulations, which we see visually as well. Then we combine significance of the data set across various thresholds and smoothing scales. We see that a degree scale again pops out as something special in the northern hemisphere. Whether we are looking at beta 0, beta 1, or they are alternating some the Euler characteristic, there is always a difference between the observation and simulation. So much so that 1,000 simulations are not enough to resolve this discrepancy. Very interestingly, then we can ask the question, if I find this, has there been a hint in the previous data sets as well? It turns out it is indeed the case. So when we look at the predecessor of Planck, this is the Wilkinson anisotropy probe map, WMAP data. This was analyzed in 2004 by Ericsson and company. And when they look at the area functional, so they look at the Minkowski functionals and the skeleton length. What they notice is when they look at the area functional and the length functional, they are usually within the 2 standard deviation band. But when they look at the genus, there is a slight deviation of genus in the positive threshold at around a degree scale, and there is a big deviation of the genus at negative thresholds at around 5 degrees. This is consistent with the results that I'm presenting over here. After this, because They were looking at full sky. So when you see a 4 standard deviation difference compared to, let's say, just over and above 2 standard deviation, you would naturally want to look at the 4 standard deviation difference. And so this degree scale anomaly was sort of overlooked at that time, which was also the case when I was looking at the full sky map. I paid more attention to the anomaly at 5 degrees compared to the anomaly at a degree scale, which is more interesting because it coincides with the physical horizon. Then we can ask the question whether it is really the whole hemisphere or it is coming from a particular specific area. It turns out that the first quadrant of the CMB is the major culprit of all this deviation. So quadrant 1 around the degree scale again is where we start noticing very big differences. So 0.005 p-value is what we are talking about through standard chi-square tests. We are not even using some specific tailored statistical methods and tests. So not trying very hard to find differences, but these differences are so strong that it is very difficult to ignore them. And with this, I will conclude my talk. The conclusion is that the CMB data exhibits mild to significant anomaly in both temperature polarization. I'm not going to show you right now. This is still under process and publication. Maybe we don't have enough time as well. It definitely hints at the violation of cosmological principle at the level of data. I'm not going to make a claim that this is really from the beginning of the universe. Because in cosmology, like Carl Sagan said, like the bigger the claim, the greater the evidence has to be. And who am I to say that the standard cosmological model is wrong? Quite possible, maybe there is some intermediate foreground effects that we don't understand. So in cosmology, we talk of 4 kinds of things that we encounter. Known knowns, so something that we know is affecting. Known unknowns, like the dark matter, dark energy. We know there is some effect, we do not know what is causing it. The unknown knowns, again, dark matter, dark energy can go in there. The unknown unknowns, we have no idea what other things may be affecting. So making a very bold claim that the signal is coming from the start of the universe, this I would not go like this has to be taken with a pinch of salt. But at the level of data, there is no doubt that the cosmic microwave background data is not statistically isotropic. Now, what problems it might cause? The problems it might cause is maybe you have heard of something called the Hubble tension and the sigma 8 tension. This is a big discussion in the cosmological field that so Einstein gave the theory of relativity. We solve Einstein's equation in so the cosmological principle, one of the reasons why cosmological principle comes in is also philosophical. Einstein's equation, solving Einstein's equation in a non-symmetric situation, very difficult. So the FLRW metric, it's a symmetric metric. To solve Einstein's equation, we start with symmetry. So isotropy, homogeneity, all of it included already in there. But what if the cosmic microwave background is not following this model that it is isotropic and homogeneous? In which case, once we estimate the parameters of the model, so we solve Einstein's equation, we get the equation for the evolution of the universe, which gives us some parameters. And these parameters, we will go back to the cosmic microwave background data, assume that this is the model it is following, and then we will estimate the parameters. What is happening though, when we estimate the parameters from the early universe, say the cosmic microwave background data, and the parameters from the late universe, let's say the galaxy distribution data set, they notice more than a 5 sigma discrepancy between these parameters. So Hubble, let's say the Hubble parameter that talks about the expansion rate of the universe, when we measure from the cosmic microwave background, it comes to around 67 kilometers per second per megaparsec. When we measure from the local universe, the galaxy, we get around 72 to 75 kilometers per second per megaparsec, and the error bars are more than 5 sigma. Now, this could be one of the potential causes. If the cosmic, I am not saying that the universe is not statistically isotropic and homogeneous, but the cosmic microwave background data is not. I do not know what the cause is, whether it is instrument error, whether there is an unknown foreground effect. or something else in between. But the end result is that the CMB is not following the standard cosmological model of isotropy and homogeneity. If that be the case, then it is not really a big surprise that this is the kind of thing, this is the kind of things that we notice. And so with this, I would like to conclude that topology and geometry are very interesting and powerful methods for analyzing data, and specifically in cosmology. But not only in cosmology, they have great applications also in biological systems. Wherever we are looking at shapes and sizes and contents and organization of structures in some sort of a system, geometry and topology can offer very powerful methods for analyzing these systems. And with this, I will end my talk.
Thank you very much. This is a very interesting contribution. So you are proposing an alternative to the standard cosmology based on the predominance of topology and some
Topological methods. I would not go so far out, Enzo, to say that I'm proposing an alternative methods. When I got into cosmology, at some point, I heard that cosmology is a religion. It took me 10 years to understand what this means. I'm too young and too small to make an alternative theory. This is why I decided to go the route of data. Proposing an alternative theory is not, that's too complicated.
Okay.
So
Just
at the moment, I'm only
suggestion.
showing that there is some discrepancy going on. And fortunately and unfortunately, actually, the more data we are gathering from the universe, the more we are noticing that there is something off. What is that something off? I think it's like the seven blind men and the elephant. We are all looking at different parts of the elephant and we are sort of saying it's a tree or a rope or a wall. Eventually, though, I hope and I think that maybe with all the pieces of this jigsaw puzzle, they will fit together eventually. But at the moment, I will not go so far out to say that I'm proposing an alternative theory about the universe. No.
Okay.
Let's stick to George Lemaitre and Big Bang Theory for now.
Your point is clear. Are there any questions about this interesting talk? Just curiosity. How did you think about Enrico Betti's numbers? They're used in specific fields. How did you think
I have a very strange trajectory. I started my master's in physics, then I went to start geometry and topology. Maybe you know the name of Herbert Edelsbrunner. Edelsbrunner was my PhD supervisor, and he brought the realm of topology into the direction of computing. So computational topology, he started it and I became his student. And then I thought, why not use this on cosmological data sets? So it was sort of serendipitous. I did not really plan to go in this direction, but it sort of happened. And then, so it's only in the last 20 years or something, 20, 30 years that Betti numbers, Enrico Betti, like you say, Enrico Betti, he wrote it in 1871. Yes. The idea starts in 1871. But it takes more than 2 centuries to bring this into the computational direction, which I think is a very deep development, bringing topology from a realm of purely theoretical science into something of a strong application. So I am really grateful to Betti, Enrico Betti, and my supervisor, Herbert Edelsbrunner also. And I also studied with Robert Adler, the guy I was telling you about. So I basically went to a lot of places meandering because I wanted to understand in depth about what are the things that I'm using, applying. So I studied a bit of cosmology, I studied a bit of topology, I studied probability and statistics, geometry, and so yeah, I like to study, let's say. So, well, that's the background.
And now you have proposed an interplay talk. Very interesting. So thank you very much, dear Pratyush. And I noticed that Tetiana Obicod should be ready for her talk. Are you ready?
Yes, I am ready.
Enzo, when I stop sharing my screen. Thank you.
Thank you very much. It has been very interesting.